All right. So today we're going to continue our lesson on chain rule, and then we're also going to continue to look at, does every problem really need chain rule? Because as we've seen in the past, sometimes we can simplify the problem and it doesn't need the method we're working on. Each time we look at a question, we should think about, can you simplify it? Because if you can, like the problem we had on the test the other day, where you divided the square root into the whole problem, turned it into a power rule problem, there are occasions in which if you can do that kind of simplifying, then it's not chain rule. There also is another little small facet of integration that we need to look at that's called, really, it's true substitution, and it's not chain rule substitution. And we're going to look at that as well today. And then tomorrow we'll focus on having the numbers on the outside, because that's not something, if Ethan's out tomorrow, that would be a problem, because he already knows how to do the first fundamental theorem of calculus. I won't be teaching anything except really just doing some more examples of the same thing with that portion added to it. All right. So, as we talked about yesterday, we have to know what U is, and we have to do the DU to see if we have it all. And we always look for what's inside is U. So what's inside of this question? Then we take the derivative of that without looking at the question. We just take the derivative of the problem we just wrote down. The 1 drops off because it's a constant. 3x squared is the power rule, dx. Because you put the power in front and take 1 off. Now I look at my problem to see, do I have any pieces of du in it? Yes, I do. I have some of it. I have a dx over here, and I have an x squared that's all by himself up here. That's right. I got to add the 3 to it and put the reciprocal out here. Now, we could rewrite this question, and it might be a little bit easier to see that u to u work if we rewrote it as 1/3 integrated and bring this up to make it look like a power problem with our 3x squared dx to the side. Because it's on top, you can move it to the side. And that's important because this needs to be over here with dx, but it doesn't need to be part of the actual part that had the inside part. So now that I've brought that up and I've got du over here to the side of it, this is just 1/3 integrating u to the -2 du, because all of this is du and the inside of that is u. Is that clicking a little better today?
No, I zoned out. I'm sorry.
Okay. So now we got to add 1 to the power, because now we're truly integrating. To make that integration symbol come off, we got to add 1 to the power. What does that now make the power? All right, so then if I put a -1 on the bottom, that really just puts the negative in front of the whole thing, right? So it's 1/3 times -1 over u. And if I go back and think about putting that together and putting back in what u is, then that's -1 over 3 with this parentheses showing that was u. Now, do you think I should distribute that? I can, but should I is what I'm asking. If you simplify it, then you don't see the u anymore. And the whole point to chain rule is usually you do want to be able to see your u work. Although, I will say, once in a while, because this is a power of 1, they might actually distribute that. But when it's a power of anything else, they probably wouldn't never multiply the power out because they want to see u. So in this lesson, we're supposed to leave it like that because we want to still see our u. All right, let's look at another one. So in number 8, I'm integrating 1 over the square root of 2x. And again, the whole point is to figure out what's inside and take the derivative of it. So what's inside my problem? 2x. What is the derivative of 2x? So that means 2 dx. So now I'll look at my problem and I say, do I have a 2 outside of that? No. I got a dx, so don't I? But I don't have a 2 with that dx. So if I put a 2 here, I have to put a half out here. Or you can put it up there, yes. I just write it with the dx because I think that's where it's going to end up. So I'm thinking about this problem really means I'm going to bring that radical up and make it to a negative half power. Would everybody agree with that? All of this is du. The inside of this is u. So you want to get rid of the fractional look, because if you can turn it into a power problem, you can use power rules to integrate it. If you can't turn it into power rules, I don't know what you're going to do, because this has powers in it. So now I'm integrating u to the negative half du. So we're going to add 1 to the power. What's negative a half plus 1? 1/2. And what do you do with that half power after you get it to make your denominator? Flip it. But I already have a half out here, so when I flip my half that I put on the denominator over and put it in front, what happens? Cancels. So I just have the square root of u, which then becomes the square root of 2x plus c. Now, if you think this through derivative-wise, this makes sense. When you take the derivative of this, don't that mean put a half power in front and take 1 off the power makes it a negative half power, and that would go down? Well, wow, it was down. And that half power that you put out in front would get multiplied by the derivative of the inside, and the derivative of the inside is 2, and that cancels it out, and that's why there wasn't a 2 on top. So it makes sense if you go back and take the derivative of the answer you get, why that canceled out and didn't have that 2 that we had to put back. All right, next one. Let's look at a trig example. There's always important to look at a trig example because we have a lot of problems that deal with trig. And as always, trig always has an inside. So that's pretty obvious that this u is 2x, and du again is 2 dx. Do I have a lonesome 2 floating around somewhere in the problem? No. I've got to put a half in front. So now what I'd like to do is I'd like to change this problem to where this piece is u and this piece is du. So 1/2 integration of sine u du. Now when you integrate sine, what does it become? Does that need a negative? Why does it need a negative? Right. See, the derivative of a cosine is supposed to be negative sine. So if you just remember, the rule says when you integrate it, if it starts with a c after the integration, put a negative on it. So negative 1/2 cosine of 2x plus c. Because we're going to put the u back in. Yeah, I think so. I think it's a little bit more complicated because there's so many algebra rules you have to work with. But trig's very simple. Most of the time. All right, so in question number 10, the inside is x and the derivative is 1 dx. But is that really how I should be going? Yeah, this problem is not chain rule. And how I know is because the derivative of the inside of this problem is not sitting on top. The derivative of x is 1. Does that look like a 1 up there? Then that tells you immediately it's not chain rule. This is you've got to divide the problem out. So 2 minus 1/2 is 3/2. 1 minus 1/2 is 1/2. And then there's no x's to do by this one, so that makes that power come up to the negative 1/2. See, because there are no x's, 0 minus 1/2 is negative 1/2. If you want to think of it that way. So this problem's straight out power rule. Once you divide it, it becomes a power rule. And it was powers already that we were working with, so it's all about powers. So this will be x to the 5/2 if I add 1 and put 2/5 in front. Everybody agree? That 3/2 plus 1 is 5/2? And flip it and put it in front? So what's a half plus a whole? All right. And if I flip that over in front, I got to multiply it by 3. What does that do? 3's cancel. Everybody agree? All right. So that'll be 2x to the 3/2. All right, if I add 1 to this negative half power over here, what do I get? Half. And if I flip that over and put it in front and multiply it by the 7, I get 14 square roots of x plus c. So that was straight out power rule. It wasn't a chain rule. So they try to throw one in every so often that chain rule doesn't work with to keep reminding you that not everything that has an inside is a chain rule. That what makes it a chain rule is if the derivative of the inside is outside, or if you could add a number to it and it would be there. And that definitely was too much on the top for that to happen. Now, in my next question, I have another trig one. And this one's not really any harder than the last one, but it is a little bit different because of the way it's written. So I'm integrating 1 over theta squared times the cosine of 1 over theta. So inside the trig is your u. Now if you talk about 1 over theta, what power problem is that? Negative 1. So let's talk about taking the derivative of that. So if we put the power in front, that'd be negative 1 theta to the negative 2, which is negative 1 over theta squared, d theta. I got a d theta, and I got a 1 over theta squared, but what do I not have? I don't have the negative. So if I put 1 in here, guess what? You have to put 1 outside so they'll cancel. Not that I'm going to cancel them, but that's why they're not there. They canceled out when somebody did the derivative. So now the problem really looks like this. Negative integration of cosine of 1 over theta, negative 1 over theta squared d theta. Well, all of this is du and this is u. What? Did I make a mistake?
No, I was just trying to read it.
Oh, sorry. My handwriting's not real good this afternoon.
No, I didn't know. Like on the top of the D problem, I didn't know if you were circling a negative or if you were trying to draw a theta symbol.
Okay. I circled the negative 1. I said I circled the negative. Yeah. Yeah, I see what you're saying now. It would have helped if I'd done that in a different color. Yeah, because this right here is the only piece that we didn't have. So that's why we're having to put it in both. So now we're just integrating negative integration of cosine of u du. So what does cosine integrate to? Do I need a negative on it?
No. Only the negative on the outside.
Well, I mean, another negative is what I meant. I don't need another negative because it doesn't start with a C, right? But I do keep the one that's already there. Because sometimes it might cancel out. And then you put back inside what was inside it the first time for the u. So even though this one looked kind of a little strange because they put the du part out in front of the question, they usually don't want to put it back there with the d theta. They really like to shove stuff to the front to see if you know where to move it to. All right, and then this next question, I want you to look very carefully at it, and don't answer it out loud, but think about, could you choose what's you in this problem? Because some students think it's one thing, and some students think it's another thing. So think about, if you say whatever you choose in the problem is you, think about the derivative and see if it's there. Or if that's not the case, then switch and think the other way. Has everybody got an idea of which one they think is you? How many thinks the inside of the squared problem is you? How many of you think inside the cube problem is you? All right, a few. And a few not sure? Well, here's how you decide. You say it both ways to see which one makes more sense, okay? Let's say cosecant is the u. What's the derivative of cosecant? So cosecant, cotangent. Do you see those two words side by side in here? Okay. Now let's talk about it the other way. Because, I mean, there are a bunch of them in here. Maybe we can make two side by side. I don't know. But let's talk about it the other way. Cotangent of x. What is the derivative of cotangent of x? Tyler, you with us? Okay. He's about to nod off there. What is the derivative of cotangent of x? Cosecant squared. Is that there? That's how you decide. You ask yourself the question both ways, and whichever one has the derivative there, that's the one's you.
I chose the one on the bottom. That one's the bottom.
And 9 times out of 10, you probably could go with the one on the bottom and check it first, because they usually put the derivative of it on top. So cotangent of x is cosecant squared of x. Does it need a negative? Well, the original word started with a C. When you take a derivative, that puts a negative on it. Does my problem have it? No. So that's how you decide whether the top or the bottom in this problem is you. Is you think about the inside, taking the derivative, and see if its derivative is actually there. You'd have had to have a cosecant and a cotangent side by side for that to be cosecant to you. I'm not done with this yet. So now let me rewrite the question in the correct format. So since that cosecant squared of x is du, it's got to come over here. Now that just leaves me with this denominator to the third power, right? I just took everything off the top and stuck it over here because that's the derivative. That only leaves me this, so I do what? That's right, you bring it up as a negative. See, anytime you have something in a power problem on the denominator, you're going to bring it up and make it a negative power because that's the only way you can do the power rule. So we're really integrating the negative on the outside with u to the negative 3 du because that u is inside of that third power problem. But we got to bring it up so we can make a negative power out of it and work our power rule. So now when we add 1 to it, what will our power become? And then if I put that over negative 2, and there's already a negative out here, the negatives cancel. So then it's going to bring down and make that to the positive 2 power. So these two negatives cancel, but that 2 stays down there because it's a coefficient. You only move the part that has the negative power down. That's why it's even if that negative had stayed on that 2, I would not be moving it because it doesn't move. This is a number, and numbers can't move across division bars. Only power problems can. And one of the things that I think I've seen students that don't really understand, these two things aren't together. So when you have one of them to a negative power, you only move the piece that has the power on it. So in this problem, even though these two negatives canceled or don't cancel, that 2's not going anywhere because he's not a power. He's a coefficient. And then you can just go back and substitute in what was inside, which happens to be cotangent of x. Let's see. Now, that's pretty much how chain rule works. So we're still having to write u and du work out, but sometimes du doesn't have its number it needs, and we fix that. Then we move things around to make the du part get away from the problem, because the du part does not affect your integration. It just affects the coefficients being right in front of the integration symbol that you have to add. And then you're really just integrating the outside. You're never really integrating the inside. It's all about integrating the outside. Now, I have just a little bit more. I got to skip a couple pages in my notes here and go over to these last two questions that I have that are, they're substitution of u, but they're not chain rule. And that's what my title is going to be up at the top. There's some kinds of substitution that you can do in calculus that it's not chain rule, but it makes the problem easier to work because you substitute. So I'm going to show you a couple of examples of substitution by u and how it relates to what we're talking about, but is not chain rule. And when this gets used is when the derivative is not on the outside and you can't divide it out like we did that square root of x. It's like I can't simplify the problem and get rid of something that's in the problem and it's not supposed to be there. All right, so let's look at these two examples. In number one, we have an x and we have a square root of x plus 2 dx. Now, obviously, if this was chain rule, wouldn't u be equal to x plus 2? Well, if that was the case, what would du be of the derivative of that piece? 1 dx. Do you see the problem? I have an extra piece left over in my problem I haven't used. That's why it's not chain rule. Okay? It is not chain rule. So in order to work this question, what you have to do, kind of is something that we've done in the past. When you solve systems equations, I don't know, y'all may not have done this, so let me just talk about this a minute. If you have an equation that's 3x plus 4, and you have an equation that's 2x minus 7y equals 10, and you solve them, how do you do that with substitution? That's right, you plug this in for y, so it's all x's. Well, we're going to kind of do something similar to that with this chain rule problem. But what we're going to do is convert the problem to all u's and leave it u. Because if I can convert the problem to all u's, it'll fix the issue of having something you can't work with on the outside. So let me show you how that works. So the first thing you do is you set up your chain rule look, but then you solve each one of these for x and dx. So if I solve this for x, won't that be u minus 2? Everybody agree with that? No, it'll be minus 2, won't it? Because you got to do the opposite to get x by itself, right? Right. If I take this x plus 2 and I solve it for u, it'll help if I write the right thing. That would have to be u minus 2. Would everybody agree with that, right? Because you got to get rid of subtraction to get rid of this adding here to move it to the other side. Now, if I want to solve this for dx, wouldn't I divide by 1? Oh, wow, that's going to do a lot. One on both of them, it don't matter. Now, sometimes you might have to actually physically do some solving here, but on this one, if you divide by 1, you multiply by 1, it's the same thing, right? It's not going to change anything. Yeah, because it's going to get used in the problem to substitute in the right thing. All right, so now that I've got everything set up, this is what you're going to use for your substitution. Every x in this problem is going to become u minus 2. And dx is going to become 1 du. So I'm going to take this x that I circled, and I'm going to put in parentheses u minus 2. And then I'm going to take this square root symbol, and I'm going to take out this x and put in u minus 2. And the reason I put the parentheses in there is because I needed a grouping symbol to keep that all grouped together with that X on the outside, but I don't need a grouping symbol in here because it's in the grouping symbol. And then this 1 dx is going to become 1 du. Now, let's simplify this a little bit. What do you think simplifies first? Yep. What happens in that square root? The 2's cancel. All right. Now, I want us to think chain rule now. The derivative of the inside is 1. I got that. Now, the derivative of this is 1. I got that. So it makes it to where the pieces actually have the correct derivatives for the insides now. But at this point, most of the time, what you do is you end up having to multiply it all together so you can do power rule on each individual piece. So, u times a half would mean 1 plus a half is 3 halves. Because the square root times the power of 1, you add the powers. And negative 2 times the radical is just going to be negative 2 times the radical. And 1 times du is just du, so if you don't want to write the 1, you don't have to. So I took a problem that was not chain rule, used substitution, and got the problem in all u's. That gives me the opportunity to actually use power rule now and just add 1 to the power and flip it in front. So what is the power going to become on the 3 halves? 5 halves and put 2/5 in front, right? All right, what about the half power? Becomes 3 halves, so I'll put 2/3 in front. Okay. So I need to multiply those two together and make 4/3 out of it. And then what you do is you go back and you put down what was u originally. Wasn't it x plus 2? Wow, that's a really bad 3. So the key here is by taking it and turning it into u's, we were able to do lovely power rule work, and we just go back at the end and put the x stuff back in, what u was actually equal to. And it was a whole lot easier than doing chain rule. A little confusing sometimes until you've seen a few of them, but it actually is a whole lot easier than chain rule. And I couldn't do chain rule with this problem because it wouldn't work. So I had to have some kind of method. So that's why they call this whole chapter substitution, because chain rule is a substitution method. But it's a little different substitution method than this one. All right, let's look at another example of this problem. How much room y'all got? Half a page. I mean, I took up that much.
Did you double space?
I used 2 lines for the top and bottom of the fraction. 1 line for the top, 1 line for the bottom. That's why it took so much. You could make it work a little different than that. I just thought I'd warn you because this one's a little longer than the last one. All right. So to get started, you do the same thought process that you did before. You still think about who's inside. All right. Now, what's the derivative of 2x minus 1? 2 dx. Do you see a 2 floating around that problem not being used? No, you see an x squared minus 1 floating around. Well, that's way too much for it. I got way more than I need for a derivative on top, don't I? That's why this is not chain rule. If all I needed was put a 2 on top, I could have done that. But I got x's up there I don't need. So if you got stuff you don't need for du, that's a clue that you're going to do the solving way. Now, if you put the solve stuff under this side and do the integration on that side, which I didn't do, you might not take up quite as much room. So if you solve this u problem, wouldn't you have to like turn it around and think literals? So I got to add 1. Everybody agree with that? And divide the whole thing by 2. So there's what my x is equal to. Now if I solve my dx problem, How do I get rid of this 2 on the dx? Divide by 2. So that's going to turn it into 1/2 du. Because you just flip multiply, right? It's the same thing as dividing by 2. So now we have these 2 items to plug in for x and dx everywhere in this problem. So let's substitute all of that in and see where it's going. So first, when we put in the x part, we need to put it in parentheses because it's squared. And then inside the radical, we need to put the x part in parentheses because it's a fraction. And then for dx, we're going to put in 1/2 du. Now, before I move on, let's just think this through real quick. The derivative of this, if you rewrote this question and looked at it in a little better format, wouldn't this be 1/2 u plus 1/2? 1/2 u plus 1/2 if you divided both pieces by 2. 1/2 u plus 1/2. Okay. So 1/2 u, the derivative is 1/2. And the derivative of 1/2 is 0, so it drops off the end. Look what I got over here. I've got the correct stuff in here for the derivative of these 2 insides. Does that make sense? Yeah. I have the 1/2 in the derivative that is the actual derivative of this. If you solved it wrong, if you took the derivative of this side, if it didn't match this, you'd know you did something wrong.
Oh, okay.
So I always double check my derivative work that I solved for by taking my x equal equation and taking the derivative of that side and making sure it makes this in case I make a math error, because sometimes they're a little harder to solve. Now, let's see how much simplifying we can do. First of all, want those 2 cancel. Then that makes this u plus 1 minus 1. Want the 1's cancel. Everybody agree? So now my problem is u plus 1 over 2 squared minus 1 over the square root of u. And I still got this half over here. That at some point we'll figure out what to do with that half. Now, where are we going next? Sure would be helpful if I could read my own handwriting. All my U's and 4's look the same on this page. Well, that's true. How do I get rid of it? Yep, I got to multiply it all out. Yes, ma'am. Me? Okay.
Did you take like 50?
So, based on our little interruption here, now we're back. So we can look at squaring what Ethan said. So we need to square that out. And eventually, don't we need to divide by this? Sometime we got to divide by this, we got to square this out, and we got to do something with this 1. So we got a lot of...
So when you square that, the denominator doesn't get squared, does it?
Yes, it does, because it's inside.
Would you square it and then subtract the power?
Possibly. But we're going to have to do a lot of simplifying on that top before we'll be able to do some subtracting powers with that u square root on the bottom. So square the first. Square the 1. 1 times u doubled.
Oh, darn.
Square the 2. Now, we want to minus this 1 from it. In order to be able to minus that, don't I need a common denominator? Uh-huh. And this is all over the square root of u, which we'll deal with later. Yes, we do. So now that we've got it, this minus 4 over 4, we can put the 2 constants together. Okay? So, I'll just keep changing markers. U squared plus 2u plus 1 minus 4 is -3. This is all over 4, right? Now you can pull this denominator up to go with the other denominator. You can do that. And why you can do that is because this is like the square root of u over 1. If you flipped it, wouldn't the u end up on the bottom of the square root? Well, it's already on the bottom, so just put them both in the same denominator. And I still have this 1/2 over here. What do you think I'm going to do with that?
You could get rid of that square.
No. But that would be nice if I could. But I can't. So that 2 is going to get multiplied to this 4 because he's in a denominator. And we're going to bring that out because we don't need that inside there. It'd be a whole lot easier if that 8th is out here and not in the bottom. Because now it's time to do what Cassie said she wanted to do, square root of u under each one. But I can't do that as well if that 4 and that 2 is still hanging around. So we put that 1/4 and that 1/2 together and took that 8th out because it doesn't really have anything to do with what we're trying to do inside here. Wow. My 8s and my integration symbols are all looking pretty bad today. So what will the first term of the inside of this integration problem be if I take and reduce the first one? U to the 3/2. What will the next one be? 2u to the 1/2. And what will the last one be? That's right. You just bring it up, make it negative 1/2. So now you have a problem that you know how to work. You know how to do power rule. You know how to add 1 to all those powers and flip it and put it in front. Now, at some point in time, I'm going to have to put this back through. At some point in time. But I think the best thing to do first is add 1 to the power and flip them and put them in front. Then multiply that to your coefficient as you put your x's back in would probably be our best bet if you don't want to have to choose about 3 or 4 more steps. So let's just leave that 8th out there for a minute and think each one of these 3. What will 3/2 become? 5/2. So we're going to flip it in front and put 2/5. What is 1/2 going to become? And I'm going to flip it in front and put 2/3. What is negative 1/2 going to become? 1/2. And I'm going to flip it in front and put 2/1. Now, as we go this time, we want to multiply the coefficients and replace u with what u originally stood for. I'll do the first one. 2 will go into that 8 4 times, right? You could do it that way, or you could say 1 times 2 is 2, and 5 times 8 is 40, and 2/40 reduces to 1/20. Does everyone agree? That might be a better thought because you got to use the 1/8 with each one. Then you put back in what was inside originally in this question. And originally it was 2x minus 1 inside. Because that's what u was. Now, talk me through what do you do with the next one. You got to do 1/8 times 2 times 2/3.
1/6.
How'd you get it?
1 times 4 over 8 times 3 then 7.
1 times 4 on the top because the 2 2's make a 4. And 8 times 3 is 24. And 4 over 24 reduces to 1/6. 6, parentheses, 2x minus 1 to the 3/2. All right, what about the next one? What about 1/8 times negative 3 times 2? 3/4, because that's 6 over 8. And then what do I do about u to the 1/2? Put a square root symbol with the 2x minus 1 back in there and a plus c on the end. And why do all these again have plus c?
Because you don't have anything to do.
That's right, you have no numbers for a and b. You're right. And I just realized I didn't put the last 2x minus 1 in. I wrote u on my paper.
Where was you recording that?
I think so. Yeah. I had to minimize it so I had somewhere to write. So this kind of substitution is kind of long.
Can I have your attention, please?
All right. So, so this kind of substitution is just a little bit different, but without it, we would have no way of working these questions. So it's good that this substitution method that's not chain rule does work really well. It just takes a lot of algebra, but it works.
The whole page is one problem.
Yeah, sometimes. All right, so what we're going to do next is I'm going to assign y'all some questions to do out of the book that relate just to this part that don't have numbers on the outside. And I'm also going to, while I'm at it, make sure that everybody understands what the directions mean. So after I tell you what you're going to do, go get your book and I'll tell what the directions mean. All right, this is page 296. This is 4.5 lesson, page 296. Basically, we're going to work from 2 to 26, and then we're going to skip a few. And we're going to do 34 to 44, and then we're going to skip a little bit. And then we're going to do 48 to 54, but it's all even. So I skipped a problem here and there because the directions are different, and they're not something I'm wanting to focus on with this lesson, although we'll come back and focus on that later. Now, if everybody goes and gets their book, we can talk about each set of directions to make sure everybody understands what the directions mean, because a couple of them are, well, I think you'd know, but just to make sure.
Well, they're going back.
Oh, let's see.
Now, some of these problems, I actually chose odd problems out of the book to do for the notes on a lot of them. So, you know, if you get stuck on one, look at the odd one next to it. It might relate, and then again, it might not. So turn to the page 296, and we'll just quickly talk about the directions. Definitely for a couple of these sets, because it's very important. A couple of them is kind of vague, but I think we'll be all right if I just talk about each one. Okay, on page 296, the very first set says complete a table by identifying U and DU, and you don't really have to make a table for that. But all they're asking you to do is write U equals DU equals, and you're done. So take the stuff in the inside out. Yeah, just take the stuff on the inside out, write out that's U, take the derivative, say it's GU, and you're done. So those three questions won't take long. Then from 8 to 26, you're actually working chain rule probably on most of those questions, but be careful. They may have thrown one in that will divide out and doesn't need chain rule. Then you've got your trig problems from 34 to 44. So we've seen some of those. And then this last set says evaluate the indefinite integrals showed by example 5. That's what I did on the last two questions. The substitution, but this not chain rule, is example 5 in your book. All right, any questions about what I've assigned? We good? All right. Now, I skipped some questions in here, and I'm going to stop the video because you don't have to know this part.